Okay, so here's where we were last time. We were talking about the sort of the ambiguity of notation, and this is just something to be aware of. But it's just not immediately obvious what that means. So just keep that in mind. If you intend that as r comma theta, maybe write r comma theta equals 1 comma pi over 6, something like that. Just be aware of the it's not perfectly obvious what you mean. Okay, let's talk about converting between these coordinate systems, rectangular and polar. Some of the formulas that you need are right here on the previous page. If you know some polar coordinates for a given point, the rectangular coordinates come straight out of this formula, plug and chug. R cosine theta is x, R sine theta is y. Going the other way is a little bit awkward, and you want to be careful about it. So now there's a temptation to look at these formulas and say, look, I can solve for R, I can solve for theta. Well, but not really, right? I mean, so there are two different values of R that will satisfy that equation. There are infinitely many values of theta that will satisfy this equation, right? So which ones do you pick? Now there's temptation to say it doesn't matter, right? Points have multiple polar coordinates, so pick one, doesn't matter, it's all fine. It's not quite so. So my favorite example along these lines is to look at this point right here, -1, -1. And if you take these x's and y's and just kind of plug them in here and, not thinking carefully at all, and just plug in and take the most obvious values that you can think of for r and theta, what you will find is that you get these two numbers here, square root of 2 for r, pi over 4 for theta. And that point is over here. Right? So it just doesn't work. It's just not as simple as we would like it to be. Right? So you've just got to think about, think carefully what are the different possible values, and then how do they group up. So, for example, now do notice that for r, there's really two different values, plus or minus, square root of 2. For theta, there's kind of two values in the sense that it's either pi over 4 or 5 pi over 4. But I say kind of two because, of course, you can add 2 pi to any angle and absolutely nothing happens to it's really morally the same direction, right? So I'm going to say, though, asterisk, two different values of theta. And the thing is, they just pair up in an unexpected way. To get the point that we're looking at there, you can think of this as 5 pi over 4, magnitude square root of 2. Right? That gives you the right point. That's fine. Or you can think of it as pi over 4, and this is weird because you think pi over 4 is in that direction, but with r of negative square root of 2, that still gets you back to the right point. All right, so anyway, don't be too casual about converting back to determining polar coordinates. Okay, all right. Okay, a couple of quick examples, and I don't want to spend a bunch of time on this kind of stuff. This is, remember we have to make some tough choices in this course. It's packed full of material, and we just have to make some tough choices about what to spend class time on and what to leave for y'all to read on your own. So I'm going to largely leave details on polar coordinates to y'all. But some easy examples. Let's look at the equation. Here's an equation in polar coordinates. R equals 3. Pretty easy cell, but that's a circle of radius 3 centered at the origin. Okay. What about theta equals pi over 3? Well, that determines, you're going to want to say that direction, but do keep in mind r can be positive or negative. I missed. And so therefore, you get this whole line. So a couple of freebies. Sometimes it's a little bit weird. I did notice some typos in here this morning, so by the way, please make those corrections. That should be square root of 2 over 2. That should be square root of 2 over 2. That said, you can kind of start plotting points and plug in theta equals 0. That gives you r equals 0, and that gives you that point. And then kind of keep going. Keep increasing your value of theta. Plugging in those thetas gives you different values of r's, and following the instructions, for these values of r, you get these points like that, and then you can kind of trace it out, fill in the blanks in between, and it's you can persuade yourself that it starts off something like that, and then by the way, keep going, and as it turns out, it makes a 4-leaf clover, which is kind of fun. Wacky. Whoops. Let's see here. I didn't mean to take that off. Another example. I'm going to let y'all read the details on this one, but weirder equation: r equals 1 plus sine theta, and again, think about different values of theta. Plug in those different values of theta, you get different values of r that come out, and that traces out a curve. This one ends up looking like, it's kind of a odd little, I'm not sure what that looks like exactly. Kind of an upside down heart, maybe. Something like that. Okay. All right. What's the algebraic version of these things of this sort? If you have an equation r equals 3 and you want to convert that into rectangular equations, for obvious reasons, right? We're familiar with rectangular equations. How do you go about doing that? Different kinds of tricks that you can use. In this case, starting with r equals 3, just square both sides, and then take advantage of the fact that we know r squared is x squared plus y squared. And then notice, as required, as we were hoping, we got a rectangular equation here. Okay, so that's nice. Okay, what about theta equals pi over 3? Well, let's take the tangent of both sides of that equation. That gives you this equation, and then don't forget tangent is y over x, when x is not 0. So that motivates this equation. And as expected, this is the equation of a circle, that's the equation of a line. So this all worked out very nicely. Sometimes it's a little trickier. What would you do with r equals cosine theta? Here's the trick in this case. Multiply both sides of the equation by r. There is a temptation to square both sides, right? When we saw an r previously, we squared, and that turned into an r squared, which was something familiar, and, yay, it all worked out. But if you do that here, yes, the r turns into r squared, but then the cosine turns into cosine squared, and what do you do with that? That's not something that we easily know how to relate to x and y. So, clever variation, multiply both sides by r, and that turns into something familiar, and that turns into something familiar. And now you've got an algebraic foot in the door. We're in rectangular coordinates at least. You do still have to complete the square to get down to the more recognizable equation for this circle, as it turns out, right? By the way, an underappreciated bit from Algebra 1 class. Completing the square. So I encourage you to make sure that you know how to do a completing of the square. If you're not, feel free to ask me in office hours. I'm sure there's help online for that kind of thing as well. But I think it's a good thing to make sure you know. Okay, not hard. This example here I'm going to skip. You're welcome to look at this one if you'd like. It's a pretty tricky version of what we talked about before. It requires knowing the angle addition formulas and making a really tricky insight. Again, given the trade-offs and considerations of what we have, time to actually talk about in class, I don't think this one quite makes the cut. If you're looking for a hard example, this would be a good one to look at. Okay. All right, so that's polar coordinates. Cylindrical coordinates is, I'm going to say, kind of the same thing. It's literally the first two coordinates of cylindrical coordinates are polar coordinates. They are, in fact, just the polar coordinates theta and r that you get by taking your point in space and projecting down to the xy plane. If you have a point in 3 space, you can look at its shadow down in the xy plane, and that point has polar coordinates in the xy plane. Those are the first two of your cylindrical coordinates. So, what about the third coordinate? Well, the third coordinate just says, how high was that point before I projected it down? In other words, z, the same exact z that we had from rectangular coordinates, and you sort of tag that on at the end, and that's called cylindrical coordinates. There's not that much to say really about cylindrical coordinates. Some people call cylindrical coordinates polar coordinates in R3, and I think that's fine. Yeah, a little awkward, but that's a good way to think about cylindrical coordinates. Okay, so sure, some examples, just to, so we can have said we did some. This equation, that's the equation of a circle in the plane, right? But if you think about it, in R3, any point whose x and y satisfy this equation, no matter what z is, also satisfies this equation. And so in some sense you can change z however you like. In other words, you take this circle and you drag it parallel to the z-axis, and all those points still work. So what do you get when you drag a circle? You get a cylinder. Okay. All right. A sphere, well, keeping in mind that this, cylindrical coordinates is polar coordinates in R3, right? X squared plus y squared is r squared, just like it was in polar coordinates. Not hard to check directly from those formulas for x and y. Right? And so this rectangular equation for the sphere becomes this cylindrical equation for the sphere. Okay, there's as many examples as you please of this. We're going to stop at this point because, again, tough choices, time's valuable, so I'm going to let you all read up on the rest of cylindrical coordinates. We're going to move on now to spherical coordinates. This one is not the same. By the way, this is another one that a lot of students call polar coordinates in R3, and I think that's a mistake. I would not think of this as polar coordinates in R3. It has something in common with polar coordinates, sure, right? But it has enough different that I just don't think that's a good label to put on it. If anything, between spherical and cylindrical, no doubt cylindrical has more in common with polar coordinates, right? So the label belongs with that one. This one, let's just call it spherical coordinates. Okay, so here's how it works. If you have a point here in space, rectangular coordinates, like so. I'm just going to do a quick double check, by the way. Did I actually start? I did start the recording. Okay, good. I couldn't remember for sure. Rectangular coordinates, x, y, and z. Here are the spherical coordinates. You have to, I guess I'll do this in yellow, you have to think about the half plane hinged on the z-axis that contains that point. And then the spherical coordinates are the following. That distance, rho, that angle measured off the z-axis, phi, it's Greek letter phi, and then this angle, theta, which, by the way, is good old theta, right? That one is, in fact, yes, it's the same theta from cylindrical coordinates. Looking at the projection down into the xy plane, it's the what you might call the polar coordinate theta in the xy plane. So, okay, sure. All right. So this is called spherical coordinates. To clarify what these funny little symbols mean, so I helpfully noted there that is the Greek letter rho, and then my intention was to helpfully indicate that this is the Greek letter phi. And as I was writing this, I was thinking in my mind phi, and then I just wrote phi. And I could correct it, but I think it's pretty funny, and so I leave it in there. But so just to be clear, so this is typically spelled in English phi, P-H-I. Okay. All right. So that's the second of the spherical coordinates. All right. Is everybody on board? Any questions so far? Okay. Right, so what does this have to do with rectangular coordinates? Well, there are formulas here for the rectangular coordinates. Here they are. Let me circle this better. Those are the conversion formulas. If you know the spherical coordinates, you want the rectangular coordinates. There you go. Now, how do I know that those are true? There's a picture that you can draw and play trig games, is the short version, and I think everybody should be good at this. Make sure that you can do this. The big hint, the thing that makes this all kind of fall into place, is to make this realization that looking at this triangle here, that distance is rho. So looking at this triangle, that distance is r. So it's not hard to persuade yourself. I mean, look at that triangle I have highlighted in yellow. It's a right triangle, and we have phi right here. There's phi, which means that angle is phi. And it's just a flashback to high school trig to see that distance r that I have in green there is rho sine phi. Quick high school trig observation. Right? So once you make that realization, the first two formulas fall in your lap. This first formula, that's really just r cosine theta again. Just, rewriting r in spherical coordinates. And this second formula, that's just y equals r sine theta again. It's the exact same formula. Just, we've rewritten r as rho sine phi, again, per this yellow triangle. Everybody see what happened there? I mean, I think it's a great way to think about it. It's a great way to memorize these formulas. Just realize that the first two of them are a rip-off of old formulas based on that yellow triangle. The third formula, not quite, but then you look at the same triangle and realize that z, again, high school trig, rho cosine phi. Okay, so it's a nice way to think about it. I encourage everybody to take this point of view, and but certainly, at a minimum, make sure that you know these formulas. I think that the ideal is to know how to derive them, just in case you forget, right? But to have them memorized for maximum, speed, convenience. So you don't have to rederive them every time. I don't think either one by itself is good enough. I don't think it's good enough just to have them rote memorized and not know where they come from, not be able to rederive them. Because the time will come, be it before our final exam or after our final exam, that I don't know, but the time will come when anything you rote memorized in this class will disappear from your brain, right? And if you understand where they came from, then you can rederive them as needed. Okay. Alrighty. Some other conversion formulas, if you want to go back the other way, you'll notice here that rho squared is x squared plus y squared plus z squared. Right? Another easy trig argument. Okay. The sphere. Rectangular equation there. Spherical equation there. It's a nice example. This shows why spherical coordinates is pretty nice in some cases, right? Look how easy that equation is in spherical coordinates. Okay. How we're going to cash that in, we'll see soon. Okay. So this next example is we're not going to do the whole thing. I'm going to do about half of this example and leave the rest again for y'all to think through on your own. The point to this is that just like polar coordinates, spherical coordinates are not unique. And in some sense, every point has infinitely many polar coordinates. Every point has two polar coordinates in some sense, and then plus or minus any number of 2 pi's as much as you want. But there's kind of the positive r, and then there's the negative r. Well, every point has kind of, in some sense, 4 spherical coordinates. Yeah, you had a question out in the back.
Just like, I'm sure you'll probably explain this, but I know, it's pretty, that's just conceptual, but will there ever be a question where we need to list all 4 possible
This is what I like to call mathematical weightlifting. So the purpose of this is to make you good at thinking about spherical coordinates, right? And I mean, weightlifting case can be made, makes you stronger, right? The case against weightlifting is that you go and you pick up a heavy thing and you expend all of this energy and you put it right back where it was in the first place. It's the most useless process in the world, if you think it from a certain point of view, right? So So think of this as an opportunity to get better at thinking about how spherical coordinates work. That's really the point here. Does that make sense?
Yeah.
Yeah, cool. All right. Okay, so let's go through a couple of these. By the way, another typo I noticed. This should be 1, not 1/2. I think when I wrote this example, I changed my mind as I was writing it out. I forgot to go back and change that one little bit. But anyway, you can see y is equal to 1 is what I got drawn in the picture here. Okay, so with x square root of 3, y equals 1, z equals 2, you can see we've got this picture. That's square root of 3, that's 1, that's 2. We've got some triangles that we can draw in here. Right, this is not only a right triangle, but a familiar right triangle. That's a 30, 60, 90. Right, y'all remember those from way back? And then there's this other triangle right here, which, as it turns out, is another familiar right triangle of 45, 45, 90. So you make those observations, and not hard to deduce that this angle in here is pi over 6, and this angle here is pi over 4. Okay, and with those observations, and this magnitude, by the way, 2 square root of 2. Okay, so we just did a little trig and a little geometry, but that allows us to get started on writing down spherical coordinates. So let's do that for this point. We're going to start off with the easy one, sort of the obvious way to think of this point in spherical coordinates, and that is to think of this point as being in that half plane hinged on the z-axis. That angle being pi over 6, and so start with observing that theta is pi over 6. Yeah. Next, well, we've already observed that angle, that's our phi, is pi over 4. Now, don't forget, you can always add 2 pi to any angle, and it doesn't change the direction. So, plus 2 pi, 2 pi n, with the understanding that n is an integer, is just a fancy way of saying add all the 2 pi's you want, subtract all the 2 pi's you want. Who cares? Likewise, 2 pi n. Okay. And then, with those 2 directions lined up, so that indicates now that we're talking about that direction, and with that direction defined, how far do I go in that direction? Well, that distance is 2 square root of 2, and so rho 2 square root of 2. And there's our first set of spherical coordinates for that point. Yeah. But it's not the only way to do this. So here's a different way to write, perfectly legitimate spherical coordinates to describe this point. It's going to seem a little weird, right? But this point, now I drew this half plane previously. Let me just point out the other side of that half plane, kind of over there, and let's think of that as being the theta direction, if you will, right? At which point theta is now, well, it's the pi over 6 that I had before plus another half turn. That makes it 7 pi over 6. Now you might say, well, you're going the wrong way, right? You're going the wrong way, and when you make a choice of phi is going to have you going down sort of that way. And that's kind of true, except phi does not have to be positive. Phi can be negative, and with a negative choice of phi, negative pi over 4, that gets me going in the correct direction. Now, having turned around and then leaned back, I am still pointing right toward that same point. And so rho, again, 2 square root of 2. Okay, so there's all sorts of little, geometric gymnastics that you've got to go through to think through the other alternatives. I think this is a healthy exercise. Again, it's a good little bit of mathematical weightlifting, so I want you all to think through these and persuade yourself that these also work. And other than the 2 pi n, 2 pi m, funny business, these are the 4 different ways to write this point in spherical coordinates. Okay, all right. Good exercise. A couple of neat applications. One application comes from observing that spherical angles are pretty darn closely related to how we keep track of location on the globe, on the surface of the Earth. Right. So notice. Let me finish drawing the Earth here. So there's my Earth. Right, and then we've got the prime meridian, let's say like that, something like that, right? Well, how do we measure east longitude? Well, east longitude is measured like that. It's measured the same way theta is. So in fact, theta, the spherical coordinate theta, can, with this setup, with the sphere drawn this way, oriented like this, choices being made like so, theta is east longitude. Right? Now, what about phi? Is phi the same as north latitude? Not quite. This is a little weird, I'll confess. Phi is measured, from the z-axis. It's measured kind of from the North Pole, and that's not how we measure latitude. We measure latitude from the equator, right? But not hard to persuade yourself looking at this picture like this that okay, well, then what that means is those two angles always add up to pi over 2. So phi is pi over 2 minus north latitude. So they're not exactly the same, but converting from spherical angles into map angles, longitude and latitude, is really quick. Right? There's nothing to it. All right. So, for your consideration, yeah.
Does that
I can't hear you. I'm sorry.
Does that equation with phi mean that part of this it can be away from the x? It's just
no. So I see where you're coming from, though. So north latitude. So the idea of north latitude is let's think of latitude as a number with north being the positive, right? So then negative latitudes would be, southern latitudes we would think of as negative north latitudes. So phi could be as big as pi over 2 in this setup. Yeah, I'm sorry, as big as pi. As big as pi. In other words, the whole south is there just with negative values of north latitude. Yeah. Okay. All right. So what can you do with this? So we have phi and theta made sense out of in this context. Notice that all points on the surface of the Earth are the same distance from the origin. Right. So rho is always just the radius of the Earth, right? Which is approximately that, 3960. By the way, a little side note for your consideration. Do you know the Earth is actually not a sphere? And not just because it's, got bumps on the surface, right? But in fact, it's quite a bit out of round because of the fact that it is rotating, right? And just like, if you take a Nerf ball or whatever, something that has some mass to it but it's kind of squishy, a water balloon would be a great thing to do this with. Take that water balloon and throw it up in the air, but give it a twist, give it a spin, and that water balloon will kind of pancake out quite a bit. Well, the Earth does too, to the tune of quite a few miles. I don't remember exactly, but I think it's on the order of plus or minus like 20 miles or something, which is not a lot over the scope of the 4,000 that we're talking about, but still, yeah, kind of interesting. Okay. So this leads us to I think a really nice application, which is how would you compute the distance between 2 points on the surface of the Earth if you have, let's say this point here, right? But then you have another point that has a different theta and a different, I don't know, maybe something up here. Different theta, different phi. Same row, of course. Right? How would you compute the distance? Well, and be careful, you can't just use the Pythagorean formula. That would have you tunneling through the center of the Earth, right? Not a practical number of interest. Right? So how would you compute the distance along the surface of the Earth? And this becomes, seemingly a hard geometry problem, because it's not like we're going straight south and then, straight east or something like that. And even if we did that, there is no Pythagorean equation, because that's not a triangle. Everything's all curvy. Right? So this is a hard problem to figure out what that distance is as the crow flies along the surface of the Earth between 2 points. And it's not irrelevant either. If you're running an airline, you need to know how far it is between 2 different points, because you're flying between those 2 different points. So a very interesting question. And here's a very convenient way to do it, and that is to observe that if you know longitude and latitude. Right, well, it's not hard to convert, as we saw above. Longitude and latitude you can convert into spherical coordinates. Once you know spherical coordinates, it's pretty straightforward to convert into rectangular coordinates. You got to do a little bit of trig, write some things down, but not that big a deal. So think of these points that you have. Longitude and latitude gives you spherical. Spherical gives you rectangular. Think of these points as having locations with rectangular coordinates. Once you know rectangular coordinates, you know how to compute dot products. That's easy. Dot products and rectangular coordinates, no sweat. And then keep in mind that when you have 2 vectors, the dot product tells you some information about the angle in between them. Right? Old formula from chapter 12. And so all this stuff can be computed. It's just simple arithmetic. And at the very end, you do have to take an arc cosine, but that allows you to compute that angle. I think that's kind of cool. Okay. Alrighty. Again, you can convert equations from rectangular to spherical, and likewise backwards. So one quick example, if you have this equation right here, so now easy to recognize that that's a sphere. This is the equation of a sphere in rectangular coordinates. Suppose you want that equation in spherical coordinates. How would you get that? No big deal. Multiply it all out. Right? Recall this conversion formula for spherical coordinates. Right? Remember that x is rho sine phi cosine theta, aka r cosine theta. And solve for rho. And there you go. There's your spherical equation for this sphere. Okay. All right. Okay, so we talked about 3 different coordinate systems. Why do we do this? Well, it turns out that this is a great way to do integrals. I remember we just got through talking about change of variables not long ago. Change of variables has this kind of hitch in it, and that is, how do you know what's your change of variables function? Sometimes you get lucky and can kind of figure it out from context. But when we were talking about this, I made a reference that there are certain functions that are just super useful as change of variables functions. And what they are is they're the change of coordinates formulas that we've just gotten through talking about. The polar coordinates conversion formula is a fantastic change of variables function. Likewise, cylindrical coordinates, likewise, spherical coordinates. So we're going to start with polar coordinates, and I'm going to try to explain how you would use polar coordinates as a change of variables function. Quick reminder, that's kind of strategically anyway what the polar coordinates function is. X is r cosine theta, y is r sine theta. Don't think of this as a couple of equations. Think of this as a formula that allows you to take polar coordinates r and theta, and then by way of these formulas, what you get out are these coordinates, x and y. So both of these are different ways of thinking about the same point, right? It's still, right, I mean, theta is still that and r is still that, right? But you can think of r and theta as being variables on their own little axis system over on the left. And that, this is just, going for, this function goes from r theta space, you might say, into xy space. Okay. All right. So if we're going to use this as a change of variables function, I claim this is going to be really useful, and we're going to see some great examples. Probably not quite today because we're going to run out of time, but certainly on Wednesday. If you're going to use this as a change of variables function, you need to know the stretching factor. Stretching factor is always computed by that formula. There's some partial derivatives in there. These are easy partial derivatives to compute. Exercise for y'all to do on your own. Got to take the determinant. Don't forget about the fact that we have this annoying absolute value, but look how simple that result has turned out to be. It's the absolute value of r. That's your stretching factor. Here's another piece of great news. This change of variables function is super useful and yet always the same function, right? The polar coordinates function is always exactly this, and so you only have to do this calculation once in your life. And having done it and having arrived at this correct conclusion, the absolute value of r, you don't have to do it again. You just memorize it. So please do make sure to memorize that. Okay. Now I have a piece of advice related to this. I suggest that you make this little promise to yourself that when you're using polar coordinates as a change of variables function, just promise yourself you'll always choose among your many options for how to describe points in polar coordinates. Just make sure to always choose r to be positive. You can always do that. You kind of always want to do that anyway, right? So this is a big win-win situation. If I choose to always do what I wanted to do anyway, namely think of r as being positive, then I get the advantage of getting to lose the absolute values, which I also wanted to do anyway, right? So it's a real two birds with one stone situation. Anyway, you do have to remember that you are now obligated. If you want to use this formula as a stretching factor, you can no longer choose negative values of r. Not that anyone wanted to anyway. Okay, so the big idea then is to notice that the bounds, let's see, I have a few seconds. Let's use this. The bounds are visible in the xy plane. So let's suppose we're looking in the xy plane at a region that looks like this. That would be a bummer of a region. If we were, going to slice it up in the usual way, because we're going to hit all sorts of corners. You're going to hit that corner and this corner, and yikes. Okay, so I make the observation that this region is bounded by these two curves, which are straight lines in the r theta plane, and it's bounded by these two curves, which are straight lines in the r theta plane also. So nice pullback. When we do our pullback integral, using this as our change of variables, our new domain is going to be a rectangle, and isn't that nice? And then you can take this region, our new pullback domain, and you can slice this up in the usual way, right? So theta starts at theta 1, whatever that value is, and then slice, and it ends at theta 2. Right? And then for a given value of theta, whatever theta you might want to fix, then where's your r start? Well, r starts at that point. That point's on that curve. That curve has that equation. There's my starting value for r. In my slicing, I end at that point. That point's on that curve. That curve has that equation. We end where r is equal to r2. And I am now out of time, so I'm going to stop there, but we're seconds away from a key observation about how to make this process even simpler. Talk about that next time, and y'all have a good Monday. See you Wednesday.